So this is next lecture of VLSI design. Here we will discuss about the oxidation process, which is one of the most important process in VLSI fabrication. So the advantages of silicon dioxide. Actually, when silicon is exposed to oxygen or oxygen with water vapors at elevated temperature, it is oxidized, and this oxide is known as silicon dioxide, and it has very important role to play in IC fabrication because it can itself be used as a diffusion mask. That means we can create, as shown in this figure, we can create a window where some area of the silicon is protected with silicon dioxide, whereas where the silicon dioxide layer is not there, from there a diffusion of impurity can take place. So it is acting as a diffusion mask in this figure. Second point is that it acts as it is used for surface passivation. That means it creates a protective layer over the entire area where it can protect the components from moisture and atmospheric contaminations. It also is a good insulator, and it has relatively high dielectric, and we also know that it is used as active gate electrode in MOS devices. Another important point is that it can be used to isolate one device from the another on a chip, and this isolation is quite good, and it is electrical isolation, which can further be used for multi-level metallization in VLSI chips. And it is rightly said that we are fortunate to have silicon and further a good silicon dioxide which can be easily made and is very stable as compared to germanium oxide. And the reason behind this is that silicon lattice is actually 40% more densely packed as compared to germanium lattice. That is why when we create oxide layer on silicon, it is more stable as compared to germanium oxide. So what is the process? The process is known as thermal oxidation. It is oxide growth process. Silicon dioxide is also known as silica, and the simple formula is that when silicon is exposed with oxygen, a solid layer of silicon dioxide is formed. Also, it happens in presence of water vapors, and we can see that the rate of oxidation is much more higher uh, in as compared to when it is done in presence of water vapors as compared to when it is only oxide based. Okay, so the rate of oxide growth using water vapor is 4 times faster than that of oxygen. This is due to the fact that actually H2O molecule is one half of the size of that of O2 molecule. So rate of diffusion of H2O is much greater as compared to O2 diffusion rate. This is usually the growth property of oxide layer on silicon. These graphs show, you can see the time versus oxide thickness. One is for dry oxygen and other is for in presence of steam. So we can refer to these curves for a particular thickness which is desired at a specific temperature. So we can always refer to these standard curves to decide upon what temperature or time is required for a particular thickness of silicon dioxide. These figures show the uh, reaction of, you can see oxygen or H2O with silicon dioxide will create an oxide thickness of TOX, and further it can be seen that this growth of silicon is actually limited after a certain time. This is because that silicon dioxide itself, it prevents this significant, after certain significant thickness, silicon dioxide will prevent further diffusion of oxygen or H2O molecules into the substrate. Okay, so we can see that the first phase of the curve in figure B, it is reaction rate limited. That means it depends on the property of O2 and H2O in silicon, whereas after beyond certain point, which is around 30 nanometer, it is diffusion rate limited, because here silicon dioxide layer has grown significantly and now it is itself preventing the further growth of oxide layer onto a silicon substrate. And this is what is also written in this slide. So this is for your reference. You can read through it. So we can always find out that dx upon dt is certain constant of proportionality C divided by x, which is oxide thickness, and if we rearrange and integrate it, it will become x square upon 2 equal to C into T, where T is the time, and we can further derive the oxide thickness equal to x under root of 2C into T.